all about the Pythagorean theorem. So we're going to be working through these doodle notes together. And if I could have you all get out your doodle notes, they should be in the chapter 9 packet on page 221. If you look down here at the bottom, we've got 221 down there. We'll be starting today by working through some of this together. I'll give you just a couple seconds to get that all out. All right, is everyone ready to go? Flash me a thumbs up in the chat if you're ready and ran for some Pythagorean theorem. Perfect. Let's get started then. So the first thing we want to say with the Pythagorean theorem, this is probably something that you all have covered. I think you covered a little in middle school, maybe just a tad in elementary. But the first and one of the most important things with the Pythagorean theorem is that we must, 100% of the time, we must be a right triangle. So what that means is our angle, we've got our one angle down here. Our angle is 90 degrees. Now let's analyze this formula over here. So this is the most popular math formula there is. Everyone knows this one. A squared plus B squared equals C squared. A is what we're going to call a leg, and B is also a leg. We have a different name for C though. Does anyone remember what we call C? And that would be our longer side right here. Feel free to message it in the chat or shout it out.
The hypotenuse.
Hypotenuse. Very nice, Caden. Thank you. So before we get too far, I want to get a couple definitions down just so we make sure we're all on the same page. So the first definition we're going to use is the definition of a leg. A leg, legs are the two sides adjacent to the right angle. Does anyone remember what the word adjacent means? Very nice, Valerie. The word we're looking for here is next to. Yeah, and I see it from you too, Antonio. Perfect. So adjacent means next to. So we can mark on our triangle up here our adjacent sides. Our legs are these two. And we can label them A and B. Now, it doesn't really matter which one we label what, but we just need to have those two labeled A and B. So if you can give me just a second. All right, sorry about that. Now let's get our hypotenuse definition down. Our hypotenuse is the side opposite the right angle. When we're talking about geometry opposites, I noticed someone answered this for adjacent. An opposite means across from. So when we're looking at our figure, across from the right angle goes that way. And we can label that side C. The important thing here, A and B, these two can flip around, but C will always be on this leg 100% of the time. Now let's work a couple examples. When we're doing problems using the Pythagorean theorem, we have four main steps that we want to follow. Step one, we label all sides. For step two, we plug in values for A, B, and C. We're going to be plugging values into our formula, which again, I'll write right up here, just so we are super duper sure to have it everywhere. A squared plus B squared equals C squared. Then step three, we are going to add A squared and B squared. Our final step, and this is the most important one, is we take the square root to find C. This is the most important step because a lot of the time students forget it. If you don't take the square root, we're not going to get to the right answer. And then that'll just make your whole process kind of silly. Because we all want the right answers here. Let's work a couple examples with these, starting with example one. I'll zoom in a little on that. So for example one, we are finding the missing side using the Pythagorean theorem. If we look at our blueprint here, step one is we label all the sides. So I'm going to label this one A, B, and then C. Once we do that, we can check off step one. For step two, we start with our equation, A squared plus B squared equals C squared. And then we plug in our values. So we said that A equals 8. We plug in 8 squared, plug in 6 squared. Once we've plugged in, we are finished with step two. Step three asks us to add A squared and B squared. So in the chat real quick, can I have someone message me what 8 squared is? 64, very nice. And then can I have someone message me what 16 squared is? Or I'm sorry, 6 squared. 36. Perfect. Thank you, everyone. We add those together and we get 100 equals c squared. We're done with step 3. And step 4 is to take our square root. Put that in purple here. What is the square root of 100? 10. Awesome. Once we get 10, we've crossed off our square root, and we are done. Four steps, none of them super complicated, but sometimes we just need that little bit of extra practice. So to hammer it in, we've got example 2 here. Example 2 asks us to find the missing side using the Pythagorean theorem. Like before, our first step, we're going to go around and label everything. I'm going to label this side A, this side B, and this side C. After we label everything, our next step is to plug in. So we take a squared plus b squared equals c squared. And we plug in 5 squared plus 10 squared equals c squared. In the chat, message me what 5 squared is and message me what 10 squared is in that order. Perfect. Thank you, everyone. Thank you. Yeah, awesome. So when we do our squares here, we get 25 plus 100 equals c squared. So 125 equals c squared. Our last step is to take a square root. Can someone tell me what the square root of 125 is? Yeah, okay, thank you. So what you should notice is if you plug the square root of 125 in your calculator, you get a decimal, about 11.18. We do not particularly like decimals, so we're going to need to simplify our radical. Just a quick refresher on how to do that. To simplify a radical, we need to write the inside as a product of a perfect square times another number. So does anyone know, can anyone come up with a perfect square that divides 125? If you've got one, feel free to message it in the chat. Yeah, awesome. That came really fast. So we can write 125 as 25 times 5. And we notice this 125 here, that's our perfect square. So we can pull it outside of the radical, and we get 5 radical 5 equals C. And that leads us to one more definition that you'll need. And there's no space, there's no like blank to fill in. So we're just going to write it down kind of in the bottom here. Our definition is a Pythagorean triple. We say A, B, C are a Pythagorean triple if all are whole numbers. So we need all of our numbers to be whole numbers, no decimals or anything. So let me ask a question here. In example 1, do we have a Pythagorean triple? Yes or no? Feel free to message it in the chat or shout it out. Awesome. Yeah, so I'm seeing some yeses, I'm seeing some thumbs up, and we are exactly right. This one is a Pythag triple. 6, 8, and 10. How about example 2? Is this one a Pythagorean triple? Yes or no? Yeah, very nice, everyone. So I'm seeing no's here. Seeing a few no's, seeing one yes. But the answer we're looking for is no. It is not a Pythagorean triple. And the reason we say it is not is because of our 5 radical 5. Whatever we do, this will always be a decimal. And if we have a decimal, we do not have a triple. All right. Are there any questions before we move on to our next page? Perfect. All right. So if I can have you all turn your Doodle Notes page. Our next section is going to be on page 222. Going to look something like this. At the top of this page, we've got the word converse in big old letters there. Does anyone remember what the word converse means besides the pair of shoes? Okay, that's all right if not. That's why I figured I'd ask. So when we use a theorem goes A to B. So if our theorem goes like that, then our converse goes B to A. Our converse takes the theorem and it flips it around. So filling in our blanks down here, we use the Pythagorean theorem to use legs to solve for the hypotenuse we use its converse to use the hypotenuse and one leg to solve for the other leg. So our Pythagorean theorem goes from legs to hypotenuses. Our converse goes from hypotenuse to leg. Looking ahead to our next little chunk of a page. Excuse me. We're going to fill out our blanks first. So like last time, C is going to be our hypotenuse. This time, A is going to be our known leg. So that's going to be whichever leg we know the most information about. And then B is going to be our mystery leg. B is going to be whatever we solve for. Looking ahead to our shortcuts box on the right, to find the hypotenuse, we add A squared and B squared. To find a leg, we subtract C squared minus A squared. Those are the quick little shortcuts we have there. Looking at my triangle down here, if we're missing this leg length, what are we going to do with the squares? Are we going to add or subtract them? Feel free to message it in the chat or shout it out. Awesome. Yeah, very nice. We are going to subtract the squares. And then looking at my bottom triangle here, if we're missing this side, are we going to add or subtract the squares? Awesome. Yeah, very nice. Very nice. We are going to add the squares. All right, filling in our steps off to the left here. Just like last time, we are going to label all sides. Then we're going to plug in values for A, B, and C, just like last time. Step 3, we're going to subtract. This is where our big difference is. We're going to subtract C squared minus A squared. And for step 4, we take the square root to find the missing leg. Really close to what we did on the last one, but just tiny little differences. So we're going to work a couple examples here. I'm going to zoom in just a little on that. We can see those numbers a bit nicer. Yeah, that looks better. So in example 1, we find the missing leg using the Pythagorean theorem. So just like before, we are going to label first our hypotenuse, our known leg, and our missing leg. Next, we want to start plugging in. So this time, we're going to use our converse equation. We're going to take that 8, plug it in there, 6, plug it in there. We're done with step 2. All right. So in the chat, can you message me what 8 squared and what 6 squared are? Perfect. Yeah, I see it from a couple people. So 8 squared is 64. 6 squared is 36. We do that subtraction and we get 28 equals b squared. Our last step is to take our square root and simplify. Radical 28 equals b. Can I get someone to tell me the square root of 28? Very nice, Valerie. You're jumping ahead a couple steps here, but you're exactly right. So square root of 28 is not one of our nice ones. So we have to simplify it down. What Valerie noticed is that we can rewrite 28 as 4 times 7. 4 is our perfect square, and the square root of 4 is 2. Radical 7 equals b. Done with step 4. Is this a Pythagorean triple? Yes or no? Yeah, so I'm seeing a couple no's here. And y'all are exactly right. Since we have this 2 radical 7, that's never going to be a whole number. So we do not have a Pythagorean triple. We got one more example of this to work. And this piece asks us to find the missing leg using Pythagorean theorem. Just like before, I'm going to go through and I'm going to label things. Our hypotenuse is C. Our known leg is 4. And our mystery leg is B. We can then set up the equation saying C squared minus A squared equals B squared. And we plug in. So we get 12 squared minus 4 squared equals B squared. Done with step 2. Message me in the chat what our squares are. So what is 12 squared and what is 4 squared? Awesome. Yeah. See it from a couple different people here. 12 squared is 144. 14 squared is 16. We subtract the 2 and we get 128 equals B squared. Then step 4, we take our square root Can we simplify our square root? Yes or no? Yeah, so we can simplify this a little more. What we notice is 128 is the same thing as 64 times 2. The square root of 64 is 8. Keep our radical 2 equals B. My question for everyone, is this a Pythagorean triple? Yes or no? Yeah, so the answer I'm looking for here is no. This 8 radical 2, that's going to give us a decimal. So neither of these are not triples. More often than not, you will not be getting Pythagorean triples. So keep that in mind. Are there any questions, or are we free to move on to the, or are we good to move on to the next page? Perfect. If we turn the page, we hit this little area that's called proof. So before we get into this, I just want to say a quick history lesson. We don't actually know who created the Pythagorean theorem. Pythagorean refers to Pythagoras, but he actually had a whole cult of math people. And anytime one of them took credit, anytime one of them discovered it, he took credit for it. So we have no clue who the Pythagorean theorem really came from. We know that the Greeks had it, and we know that the Babylonians had it, and even the Egyptians. But we don't know who had it first. So that's just a fun little math fact there. Not relevant, but I like it. So the way this proof works is we're going to be counting squares. So if we look at our a squared box right here, we notice that we have 1, 2, 3, 4, 5, 6, 7, 8, 9 squares. I'm just going to kind of shade those in a little bit of blue. We're going to call that 9. We can fill in the 9 over here. Now, if we look at b squared, our square down on the bottom here, we have 1, 2, 3, 4, 7, 8, 9, 10, 11, 12, 16 squares. I'm going to color them this way. And we can write 16 here. And then we can also fill in 16 in this box. So now I'm looking at my big C squared. And we notice if we color in 9 blue squares, we still have 16 red squares, which gives us a grand total of 25. So 9 squared, or 9 plus 16 equals 25. Yeah, perfect. Thank you for those messaging in the chat. I appreciate it. Filling in our little blanks on the bottom, the area of the square of the hypotenuse you're going to label that C, is equal to the sum of the area of the squares of A and B. So we add A and B, A squared and B squared together, and we get C squared. Example 1 here gives us a couple practice problems. So if we say the area of the square of A is 36 and the area of the square of B is 64, what is the area of the square of C? So that's just to all of you. What is the area of the square of C? Yeah, so there it is in the chat. So what I was looking for is 100. I saw 90 in there. For my person who answered 90, check your addition on that one. So you should be getting a nice even 100 there. Moving on to our next one. If the area of the square of C is 81 and the area of the square of B is 62, then what is the area of the square of A? Feel free to message that in the chat. Yeah, awesome. Thank you. So the area we're looking for there is 19. Remember, when we're solving for the area of one of the legs, we need to subtract the two numbers, not add them together. Problems like this aren't going to show up very often, but it's good for you to have that mental idea of what a proof looks like. The last thing on our Doodle Notes sheet that we're going to talk about today is distance. Now, I know Miss Davis gave you a distance formula at the beginning of the year, but I also know that if you are anything like me at all, that distance formula is a mess. It can be tough to remember sometimes. So what we're going to talk about is how to use the Pythagorean theorem to calculate distance. So if we notice, we've got our 2 points and our segment right here. The first thing we want to do is we want to create a right triangle just by drawing our lines down and across until they meet each other. The next thing we want to do is we want to count boxes, as simple as it sounds. So if we look at our right leg, we've got 1, 2, 3 boxes. And if we look on our bottom leg, we've got 1, 2, 3, 4 boxes. Then we take those numbers and we plug them into our Pythagorean theorem. So we can say 3 squared plus 4 squared equals C squared. When we do 3 squared, we get 9. When we do 4 squared, we get 16 equals C squared. We get 25 equals C squared. We take the square roots and we get 5 equals C. You don't have to you don't have to use the Pythagorean formula. You don't have to use the distance formula, but you can choose one that you prefer. And that's the one I'd stick with. We've got one more little practice problem, which is example 2 right here. We're finding the distance between the 2 points. The first thing I would do is I would plot our points. So to plot 1, -4, we go to the left 1, and then down 2, 3, 4. And to plot 5, 1, we go to the right 5, 1, 2, 3, 4, 5, and up 1. We connect the dots. And there we've got our segment. The next step, we make our right triangle now. Counting boxes How long is our vertical leg? Feel free to message it in the chat or shout it out. Yeah, very nice. If we count our boxes there, we have 5 here, and we get 4 for our bottom leg. So we go to our Pythagorean theorem, and then we plug in our numbers. So we can do 5 squared plus 4 squared equals c squared. 25 plus 16 equals c squared. I come over here. 41 equals c squared. Square root of 41 equals c. Can we simplify the square root of 41 any? Yes or no? We cannot. This is as simple as 41 gets. So we can say our distance equals radical 41. All right. Are there any questions on this page? Okay. Hang in there with me for just a little bit longer. We've got one more page to do, and this one goes super fast. Super fast. So this is our classifying triangles page. One of the problems you will be given on homework assignments is you'll be given a set of segments like 9, 40, and 41. And then you'll be asked, is this a triangle? What type? We got a couple ways we can check this. The first thing we want to do, we want to label our sides A, B, and C. The important thing here is that C is always our longest side. And then we want to start at the top of our table. Does A plus B equal C? So does 9 plus 40, 41? Feel free to message me in the chat. Are these two equal? Yes or no? Yeah, exactly. 49 is not equal to 41. Since it's not equal, we take this branch down. Now let's say they were equal. Let's say we had been given 2, 3, and 5. If that was the case, then we would have a segment. I would look something like this. C, A, B. All right. Our next question is A plus B greater than C? Shoot me in the chat, yes or no. So, if we look and compare, A plus B gives us 49. And 49 is greater than 41. So we're going to take this yes arrow down. Now let's say we had had like 1, 2, and 4. Then we would have gone no, and we would have been an open figure. And that would look something kind of like this. An open figure happens when our sides aren't long enough to meet. All right. Now, if we move on to these bottom chunks, keeping our same sides of 9, 40, and 41, let's check these other ones. So let's say 9 squared. We want to plug in to a squared plus b squared question mark c squared. So we'll do 9 squared plus 40 squared question mark 41 squared. 9 squared is 81. 40 squared is 1600. And 41 squared is 1681. So we get 1681, question mark 1681. So looking at our question, is a squared plus b squared greater than c squared? Strictly greater. Answer me yes or no in the chat. Awesome. Yeah, so it is not strictly greater. We go this way. If it was, then we would have an acute triangle. What that means is all angles less than 90 degrees. So something kind of small, kind of short and small like that. Then we check our next piece. Is a squared plus b squared strictly less than c squared? Yes or no? So the answer I'm looking for here is no. I see a couple I see a yes in the chat. And my hint is, since we want strictly less than, they have to be, it would have to be like 1000 in 1681 for that to work. So we go no. Say we had gone yes. Then we would have an obtuse triangle. This is one angle greater than 90 degrees. Looks something kind of like this. So our last option is down here. This means if we get all the way down here, then we have a right triangle. Because if we think about it, what we did is we just kind of plugged it into the Pythagorean theorem. We saw a squared plus b squared, it's not greater than, and it's also not less than. So it has to be strictly equal. So to kind of summarize what we do in the problem like this, our first step is we check a plus b question mark c. And then we do a squared plus b squared question mark c squared. So if we check these two inequalities, that's all that we need. Are there any questions? Okay, perfect.